So let's begin with Gordie. Gordie, these are really big deals. They come in at about $15 or $20 million a piece.
Something like that.
And have been bought by major American research and corporations.
That's right, correct.
All right, Gordie.
Thank you. Hi, everybody. So quantum computing is a very technical subject, and I'm not going to talk a lot about the specific details, of which I'm glad. I'm sure you're glad. But I'm going to try to give you an idea about what the kind of thing is that we build and why people are so excited about it. But I'm going to wrap that story in another story. How many of you have children? Let's see, hands. So it's almost everybody. So I have 3 children. The youngest is 4. The oldest is 8. And they're very different. But they share one thing in common, and the parents in the audience may, I suspect, have noticed the same thing. Each of my children has fixated on a particular stuffed animal as being their special friend or toy. And in particular, my middle son, James, absolutely loves this little guy called Bear Bear, which is the picture that I'm showing up here. Bear Bear was a limited release Thai Beanie Baby, and there aren't very many of them that were made of his particular form. And one Christmas, I decided that it would be insurance policy to go and try to buy some more just in case something happened to Bear Bear. So I went on the internet and did a search, and I was only able to locate 2 others that were for sale, and I bought both of them. So now he has 3 of these little guys. But the reason that it occurred to me that this might be a good place to start is a conversation that I had with him last week. He wanted to sleep with his older brother in his bedroom, and his older brother wouldn't let him. And he was very sad and despondent, and he was like, I'm scared, I don't want to sleep by myself. And I said, well, you've got Bear Bear. And he said to me, Bear Bear isn't real. And so I found this very intensely distressing for a variety of reasons that maybe you'll understand when I go through this. And I assured him that Bear Bear was as real as anything else in the world. And he said, but he can't speak and he can't move. And so I said, well, what you really mean is he's not alive. And he said, yes, that's what I mean. So for very young children, the sense of being real and the sense of being alive are somehow connected. And I'm going to circle back to this point at the end. But before I do that, I'm going to tell you a little bit about quantum computers and why people care so much about them. There are literally tens of thousands of some of the brightest people in the world today trying to build these machines and understand them. And I'm going to tell you why. In my last 15 years of working on this type of stuff, I found that scientists divide up into 2 categories of zealots about this field. The first half are people who are absolutely entranced by the physics of these things. This quote is from a respectable scientist, in fact, one of the founders of this field, that may look a little strange to you who don't follow theoretical physics, but there is a very clear prediction that our most successful theory of nature makes, and that is that there are an enormous number, mind-bogglingly large number, of parallel realities, as real as this one, that have different consistent histories. So imagine a world where all of the laws of physics as we know them are obeyed, but different decisions were made along the way. Different decisions at the level of tiny microscopic particles, different decisions all the way up to what you chose to eat for lunch, and whether you chose to come to this session or not. Quantum mechanics makes a very specific prediction that all of those are as real as the thing that you remember. And this is bizarre, because we don't see those other things. But science has reached the point now where we can build machines that exploit those other worlds. And quantum computers are perhaps the most exciting of all of these that we have within, or almost within our grasp right now. So people from a physics background love this. They want to understand the world. They want to understand the universe, how it all works. There's another type of person who tends to come from the computer science side that's like, yeah, okay, that's all great. But there's a different thing going on here, which is just as exciting, if not more, and that these machines that supposedly can do this wild stuff, let's forget about how they work, if you could build one, could solve problems that you could never, ever solve with any computer of the sort that we built. If you took every single atom of silicon in the world and made the most sophisticated conventional Intel-style processor that you could build, there are problems we know of that I could write down on a sheet of paper that you could never, ever, ever solve with that thing, that you could with this kind of machine. So that's very exciting. Humans use tools to do things. If you give humans a new kind of tool that can do things that you couldn't otherwise do, imagine the possibilities. So you may think, well, this is all fine and dandy, but aren't these things in the realm of theory and speculation kind of in the same regime as other futuristic things you may have heard of which may be allowed by the laws of physics but aren't here yet? That's not true. There are, in fact, many of these machines deployed now in openly available research centers following the model that was used to introduce supercomputers to the world. They're too big and ornery and difficult to operate to put in your home, too expensive also, but you can give them to a place which will manage them as a shared resource that will offer that service to the world. And there are two of these now. One of them is at the University of Southern California. And this analogy with flight, I think, is an interesting one. So a horse can beat, or could beat, the initial flight of the Wright brothers' flight in speed. But a plane is not a faster horse. A plane is a different kind of machine. The plane takes advantage of another resource that nature gives us, this third dimension, in order to do something that matters to people better that you could do with any horse. It doesn't matter how fast you make a horse, it will never fly, at least the kinds of horses that we know about. So these types of computers now are being thought of in the same way. They're not terrifically powerful yet, but they're doing something completely different than what your computer does. And that thing is like flight. It gives these computers access to these new resources, maybe you could call them parallel universes, in order to do something that you couldn't otherwise do. And that's not the only one. In fact, the one I'm going to come back to and talk to in the context of the story that I'm wrapping this in was recently installed at NASA. And Google was the primary interested party that pulled this whole thing together. And this one is really exciting to me, because what they're going to do is apply this machine to an area that I think is fundamentally important. It's a crux of our future as humans, and that's, can we build machines like us? So building machines like us might be possible. I certainly believe it is. I might be wrong. But what I do know is that the types of approaches that people are taking now to build intelligent machines benefit immensely from what this machine that we've built does best. So what this center is about is applying this beautiful new computational idea in the service of trying to make intelligent machines. Now, I can't think of anything personally any cooler than trying to use quantum computers to build intelligent machines, so this is very exciting to me. Steve Jurvetson has been a longtime friend and investor in the company, and for those of you who don't know him, he's a Silicon Valley investor who's probably the smartest VC that I know of, and certainly the one that's the most attuned to technological trends. He's on the board of SpaceX, Tesla, Synthetic Genomics, which is Craig Venter's company, is trying to build artificial life, and D-Wave, and that's it. And this is his particularly poetic way of framing the difference between the machines we build and conventional computers. This is what they look like. There are two of them. These are from our lab in Burnaby in British Columbia. From the outside, they look like giant black monoliths. Big, metal boxes, about 10 feet on a side, 12 feet tall. And they are powered, they have a fridge inside them, a refrigerator that cools these chips to almost absolute zero. Just a wisp, a fraction of a degree above absolute zero. Hundreds of times colder than interstellar space. Amongst the coldest and most isolated and extreme conditions that humans have ever been able to engineer. These fridges, interestingly enough, which are called pulse tube dilution refrigerators, have a thing called a pulse tube, which emits a sound roughly once per second, which sounds eerily like a heartbeat. So if you have the opportunity to stand next to one of these machines, it is an awe-inspiring thing, at least for me. It feels like an altar to an alien god. They really are impressive machines. At the heart of this big box is a tiny chip about the size of your thumbnail. And on this chip resides all of the wonder and magic that makes this thing go. I'm not going to describe in any mathematical detail how it all works, but let me give you an analogy. In quantum mechanics, there's this concept that a thing can exist in two states which are mutually exclusive at the same time, quote unquote. And I'm using those words because the English language was developed before we had concepts to describe what these things actually are doing. But I'm going to give you a roundabout way of understanding this. Imagine that there really are parallel universes out there, and now imagine you have two that are exactly identical in every respect, all the way out to the horizon as far as we can see, down to the last little atomic detail of every single thing, with only one difference. And that's the value of a little thing called a qubit on this chip, which is a contraction of quantum bit. And that qubit is very much like a bit or a transistor in a conventional computer. It has two distinct physical states, which we call 0 and 1 for bit. In a conventional computer, these are mutually exclusive. That device is either one or the other, and never anything else. In a quantum computer, that device can be in this strange situation where these two parallel universes have a nexus, a point in space where they overlap. And when you increase the number of these devices, every time you add one of these qubits, you double the number of these parallel universes that you have access to, until such time when you get to a chip like this, which is about 500 of these bits, you have something like 2 to the 500th power of these guys living in that chip. So the way I think about it is that the shadows of these parallel worlds overlap with ours. And if we're smart enough, we can dive into them and grab their resources and pull them back into ours to make an effect in our world. Now, this may sound very odd to you and bizarre, and in fact, I am using language that a normal theoretical physicist probably wouldn't use, but this is, what I'm telling you is absolutely correct and in line with the way that these things actually work. We've been doing this for some time now, and in fact, we have our own version of Moore's Law. The doubling of the number of these qubits on the chip has happened once a year for the past 9 years. So for the last 9 years, every year the number of these qubit devices has doubled, and it will continue to do so. As a point of reference in terms of how fast these things are, in one generation of chip, the one from the system that was installed at USC to the one that Google and NASA have now, the speed of the device went up by almost 500,000. This is the kind of progress that you're going to see with these types of machines going forward. And 500,000 sounds like an abstract number, but I put up a little mental comparison here to see what 5,000 really means. 500,000 is a big number when it comes to speed. All right, so now I'm getting into the last part of my talk where I'm going to make some predictions, some dangerous predictions. So predictions are very dangerous for a variety of reasons. Often they're wrong, which is one. But I think they're important because predictions somehow are our internal desires made manifest. Predictions are about what we want to happen, maybe not what will happen. And I'm going to make 3 predictions, and all of them are dangerous in the sense that they're very unlikely to happen, maybe, but I think that there's a very good chance that they may. As an aside, I just wanted to say that at least in the Valley, Silicon Valley, and maybe in the United States in general, there's a very deep feeling of unease about the way technology has been developing. Because we have all of these vast array of very smart people, and what they're doing is crap. They're building things that cannot last. They're building things that are not important. This is a little bit of a controversial point of view, but I believe it. But I think that the reason for this is it's low-hanging fruit. Computers haven't been around for a long time. And I think that what's going to happen is that as people get more comfortable with computers, the attention will turn from the Twitters and the Facebooks to very important things. So here's my first prediction. I'm going to predict that by 5 years, NASA will have found an Earth-like planet with Earth-like atmosphere and water on it, and serious people will start discussing how we get there. And by the way, they're going to use one of our machines to help do this. So that's my first prediction. My second prediction is that this business of parallel universes is going to turn out to be very important. This picture that I've got under here is what's called a gravitational lens. When Einstein proposed his general theory of relativity, it came with a bunch of experiments that you could use to test it. And one of them was that if there was a point of light very far away and a galaxy in the middle, that galaxy should bend the light and you should see a ring. And this was eventually observed. And I think what's going to happen is somebody is going to come up with an experiment to test this reality of these things, and we're going to be able to do so. My third prediction that I'm going to end on is the most important of all. I believe that humanity is on the cusp of the most important technological, societal revolution that's ever occurred. And that's when we got to the point where the machines that we build outpace us in every respect. I don't mean that they're better calculators. I don't mean that they're better at searching. I mean everything. And I think that we're very close. And my prediction is that within 15 years, we will have machines that outpace humans in everything. Thank you very much.